Hey class, today we're going to finish out 8.2 and we're going to do part 3. This part is a lot more concept based and we're going to talk about resonance. So, how are resonance structures used? In order to answer this question, we have to understand what are resonance structures. These are structures that it occurs when it is possible to draw two or more valid electron dot structures. So again, these structures are both possible. They also have the same number of electron pairs for a molecule or ion. So let's look at an example of something that displays resonance. And that example is going to be ozone. There are actually two possible electron dot structures for ozone. First, when we draw ozone, which is actually O3, we have 3 oxygen bonded together. We are going to eventually find out that the middle oxygen's not happy, so we have to make a double bond. That double bond does not matter if it happens with the oxygen on the left, as you see here, or if that double bond happened with the oxygen on the right. You can make a double bond with any of those oxygen. And so notice all we did from the left to the right is shift where those electron pairs were placed without changing the position of those oxygen atoms. And this is a good example of resonance. Essentially, those electrons resonate or move between those two electrons, or those two oxygen. Now, because early chemists imagined that electron pairs flipped back and forth, or we use that word resonate, between those different electron dot structures, what we're going to notice, and I'll flip back to the last slide, is they use a double-headed arrow to indicate if two or more structures are in resonance. So you're going to notice right here, they put a double-sided arrow to show that both of these structures are possible. So we're going to do an example of our own, and so we're going to draw it out as if we were going to do the Lewis dot structure, and I give you a hint that there are actually 3 possible structures that can occur. So here we're going to draw it out. We have nitrogen's going to donate 5 valence electrons since it's in group 5. Oxygen is going to donate 6, but I have 3 of them, so that gives me 18. When we add this together, we end up getting 23, but remember, if we have a charge, we must take that into account. That -1 charge actually means that I've gained an electron, so I need to make sure that I add one more, and this structure will actually have 24 electrons. This amount of electrons will not change between all 3 structures in order to make sure that it's resonance. So here we're going to have 3 structures. We're going to have nitrogen in the middle of every single one of these. And then each of those nitrogen are going to be bonded to 3 oxygen. Notice here that I'm putting all of the atoms in the same spot because we want to make sure that we're not shifting where they're located. Now, in each of those bonds, we actually use 6 electrons, which brings me down to 18. And so here, in order to use those 18, we're going to make the outside happy first in every single one of these. So notice we're still doing all of these structures the exact same. When we do those 18 electrons, we're going to notice that ends up using up all the electrons that I'm given. And so I've already placed all of the 24 allowed electrons on these structures. And therefore, we must do our last step, and we have to make sure everybody's happy. On every single one of these, nitrogen is not happy. Each of these, nitrogen has 6 electrons around it and it wants 8. So you're going to look at this and be like, okay, I've used all my electrons. I must make a double bond. And then the question comes, does it matter who I make a double bond with? And the answer is no. And this is kind of how we get into some resonance structures that we end up seeing. For example, on this structure, we can say, okay, let's take away these electrons and make a double bond here. Over here, we're going to take away these electrons and make a double bond here. And then over on this structure, let's take away from this one and make a double bond here. Notice these are all valid structures. It's just wherever that double bond is located. So the last thing we want to make sure for these to be correct is since this is an ion, we want to make sure all of these have brackets around them with the charge on the outside. Every single one of these structures is considered a resonance structure, -1, of each other because they have the atoms in the same spot, same number of possible electrons used. Again, we just shifted where that double bond's at. So to display that this is resonance, we're actually going to use a double-headed arrow. And when you see NO3 - 1, which is actually nitrate, all of these, again, are possible. The second thing that we're going to end on is something called bond dissociation energies. And our question that we want to answer is, how is the strength of a covalent bond related to something that we call bond dissociation energy? In order to understand this question, we have to understand what bond dissociation energy is. This is going to be the energy required to break, that's the key word, break a bond between two covalently bonded atoms. So if you ever hear the word dissociate, you separate. So we are separating two atoms that were bonded. Typically, this energy is given in something called kilojoules per mole, or the energy needed to break 1 mole of bonds. I am going to star this because this is something that you'll need to know for your test and for your Schoology. Triple bonds are going to be stronger than double bonds. It takes a lot more energy to break those bonds. And then double bonds are going to be stronger than single bonds. So again, single bonds are going to be the least amount of energy needed to break it, while triple bonds are going to require the most energy. So a large bond dissociation energy corresponds to a strong covalent bond. And hopefully this should make sense. The stronger the bond, the more energy is needed to break it. One thing about organic chemistry is it looks at things that are based off of carbon. And carbon with another carbon can actually make some pretty strong bonds. A single carbon-to-carbon bond takes about 347 kilojoules per mole of energy in order to break it. And so organic chemistry exists because of carbon-to-carbon bonds being very stable structures. They make up the backbone of a lot of important molecules. And with those high bond dissociation energies, they tend to be pretty unreactive. Again, they're harder to break because this energy is so high. So we're going to end on a true and false. A strong covalent bond has a low bond dissociation energy. If you'd like to pause this video and see if you're right, you can. Now here, hopefully we answered false. A strong covalent bond should actually have a high bond dissociation energy. And that's the end of today's lesson. Let me know if you guys have any questions, and I hope you guys have a great day.